I hope you are able to see my screen. So, what did we study in the previous class? What was our discussions? Can someone help me out? What was the topics that we were discussing? Yeah, we studied about geostationary, right? Orbits. Then we also looked at the polar orbits, right? And it has an inclination of about 90 degrees because we are to uh, check for the polar regions, which is in the north and south. Right? Okay, we looked into this polar mount antennas and the formulas associated and the limits of visibility. As I told you, this satellite also will have the limit of visibility. So what is meant by this limits of visibility, which means at certain point of time during certain duration, they will be unseen. Okay, which means hidden from the sun's rays. So what is going to happen? Its own battery system has to kick in, and it cannot rely on the solar cells which is available. So during that point of time, the battery should be able to sustain um, the periods of eclipse. As I told you, it can last for few minutes to about 72 minutes also. Right? Okay, so the Earth eclipse, I think we all are very much aware of, and yeah, so it can last for a minimum of about 10 minutes to a maximum of 72 minutes, right, for a full eclipse. Okay. So what happens exactly, during this eclipse? So as you all know, the sun's rays, okay, you can see the sun's rays here, and then we have the Earth station here, and this part doesn't receive the sun rays because of the Earth's shadow, right? The Earth's shadow. So this whole region is actually in eclipse, and this is our geostationary orbit around the Earth, and this is the east south coordinate, okay, of the satellite, and the satellite east of Earth, so the eastern part. So I'm getting the sun rays. Fine. A satellite cast on Earth station enters eclipse during daylight and early evening. Okay, so those are called busy hours at Earth station. A satellite west of Earth station enters eclipse during night because it's in the opposite direction, right? So this part would have come here. Okay, so it's in the opposite direction for when it's in the west. So satellite longitudes which are west uh, rather than east of Earth station are more desirable. So we do not want this eclipse to happen during the day, and if it happens during the night, it's fine. So because the busy hours is normally during the daytime, right? A lot of communications happen, and we do not want to take risk of operating only with a battery, right? So the next one that is involved here is your sun transit outage. So this is with regards to the transmission of the sun rays, okay, and what can happen, okay, if there's a eclipse. So what happens to the sun rays and the impact on the satellite. Transit of satellite between Earth and Sun. The Sun comes within the beam width of Earth station antenna. When this happens, okay, uh, the sun appears as an extremely noisy source. So how do we identify normally noise? Noise, how is it identified? You would have seen on your CROs, right? Disturbances. You cannot see clear signals. So these are all the impact of noise. Okay? So because of which, what is going to happen is our transmission signal or the quality of our signal is going to get impacted. An increase in error rate is also one of the reasons or the consequences of sun transit outage, or sometimes it can totally disrupt your signal. So which means noise is much higher than the communication signal. This effect is termed as sun transit outage and it lasts for short periods. So since our Earth's revolution, okay, is in an elliptical manner, so only for short duration it is going to be very close to the sun, during which this noise is enhanced and our signals are lowered. The occurrence and duration of sun transit outage depends on the latitude of the Earth station, and it can take about 10 minutes. It can take about 10 minutes for it to pass from one point to another point. Actually, what happens, even if you see the shadow, for every 10 minutes, okay, there is a degree change of shadow. I don't know how many of you have observed it. Okay, for every 10 minutes, you can see that there is a degree of change of shadow. Okay. So next we will be looking into the space segment, and this is actually your new module, okay, your module 3, okay, where we will be talking exclusively about the space and the connections or the signals required to get connected to the satellite in space. A satellite communicates system or communication system can be broadly classified into two. One is the space segment and the other one is your ground segment. So we have two devices, one is in the space and the other one is in the ground, which we also call as the Earth station. Right? So the space segment, it includes the satellite and ground facilities. So we have something called TT&C. Now this is important. We will be always looking into this um, system, which is telemetry, tracking, and command. Okay? Telemetry, tracking, and command. So these are important things which we will be dealing with throughout this module. It consists of transmit and receive Earth stations, so which are placed in ground. The payload and bus. So normally we have seen these words very frequently called the payload. Okay, payload and bus. So the passengers here is called the payload, and the one who carries the passenger is called the bus. In simple terms, right? Okay. The equipment carried on board, that is the satellite, can be classified according to the function, the payload. The equipment used to provide the service for which the satellite has been launched is called a payload. Okay. It can be for remote sensing or it can be for weather forecasting. There are n number of applications that we have seen so far, right? So it can be even with regards to your military applications. So that's a payload. Next, the bus. Bus is nothing but the satellite bus carries the payload. Satellite bus is the platform that supports payload operation reliably throughout the mission life, okay, throughout the mission. So which means till the time it is put in its orbit. So the importance of bus is to make sure that the payload reaches from the Earth station to the space and it keeps the payload in place. Okay, so that's the mission of the bus. It helps to maintain position and orientation of satellite towards the service area. Now, when we employ satellites, okay, we also decide as to which region that it needs to be covered, right? So, due to which, what is going to happen is we will get an exact idea, right, as to which country it is covering. So, all that should be kept in mind. without which it becomes difficult. Okay, and a country will never make it satellite for the use of other countries. Of course, it can be a friendly way of dealing with things. Okay, but then normally they wouldn't. Okay, normally they wouldn't entertain other countries accessing this services of the satellite that they have actually designed. Right. It refers to the vehicle as well as the subsystems that provide the power, attitude control, orbital control, then thermal control, command, okay, that is for TTMC functions required to service the payload. So all these are needed, not only just you know designing a satellite. We have to make sure that all these services are rendered to the satellite: proper temperature, proper orbital control, it should be in proper height, okay, and it should also keep the payload safe. All these are the functions of your bus. Okay. So in communication satellites, the equipment which provides the connecting link between the satellites transmit and receive antennas is referred to as transponders. Very important section of your satellite, which is nothing but called your transponder. So this is responsible for receiving as well as for transmitting signals. So without this, it's going to be difficult, for the satellite to communicate and check for signals, transmit signals or receive signals. Okay, so just tell me, without an antenna, how will you actually pass the signals, right? It's going to be difficult. So a transponder is actually a very important device, okay, which keeps or which tracks signals and which listens to us from the base station and which sends its status from the space station, right? So this is one important thing that you have to remember. Also, you can see here the transponder forms one of the main sections of the payload, and this is nothing but the antenna subsystems. Okay, so this is one of the major thing that you can see uh, with regards to a satellite. Now just take a look at this diagram, okay, and this is going to tell you as to what and how we are designing your satellite. So at the upper section, we actually have the payload, repeater, and the antenna, right? And at the lower section, okay, we have the satellite bus. So this satellite bus is needed for, as I told you, power, propulsion. The propulsion means it should have proper uh, levels of fuels. Okay, so all this are very much needed. Then TTLC is nothing but your telemetry, tracking and control, right, and command. Right. AOCS is your attitude orbit control system. AOCS. Okay. So repeaters are needed. Why repeaters are needed? Can someone tell me? Why is it so necessary for a repeater? Yeah. Why is a repeater needed? I'm waiting for the answer. Okay, tell me with respect to your signals. Okay, you will have a low signal. In that case, in order to boost your, take Wi-Fi for example, and can you tell me why a repeater is used? I've given you the clue. No answers. Kavya, Kavya, can you tell me why a repeater is used? Kavya, you're there? I cannot hear you. Anyone else wants to respond? So we make sure that the signal doesn't get lost. Okay, so a repeater is used in order to contain the signals. Okay, fine. The next one that you can see here is your satellite power supply units. Okay, so I've just given a brief information as to what is exactly used in your power supply units. Okay, so just have a look at it. So you can see here that the primary electrical power for your electronic equipment is obtained from solar cells, right? As I was mentioning, the solar cells are very much needed because it will charge the cells, and from that, the power is actually delivered to your satellite. Individual cells can generate only small amounts of power, and therefore array of cells are to be used. So which means we'll have to look at series and parallel combinations of cells in order to deliver huge power. Now just imagine, okay, it's there in the harsh environment, it's in the space, and it has to be on its own. And when it loses its trajectory, when it loses its path, okay, we have to make sure that it comes back into its path. So which means we need to have powerful systems which can actually maneuver these payloads or satellites. So your battery is a very important parameter. If not, it gets into graveyard. Okay, fine. So here you can see you have an example given, which is HS376, okay, which is for your Hughes aircraft company. Okay, they have done tremendous efforts, okay, in the field of communications, especially with satellites. Okay, and the spacecraft is a spin stabilized spacecraft. Okay, so which means even though it is spinning, okay, it can be in stable mode. The gyroscopic effect of the spin is used for mechanical orientation stability. Now, can you tell me what is this gyroscope? You would have seen this extensively, right? And can you tell me where have you seen this gyroscope? You are using it, in fact, day to day. Students, I need responses. Okay, where do we use gyroscope, or where have you seen gyroscopes? Jitender, Jitender, do you have an answer for that?
So we use gyroscopes in mobiles,
Exactly, and how is it used?
like whenever we spin the mobile or rotate it, it
Hmm.
detects the.
Exactly, right. So this is one important thing that you have to remember. So gyroscopes are actually kept for stabilizing things, right? Thank you, Kishan, for responding. Okay. So the spacecraft is 216 centimeters in diameter and about 660 centimeters long. This is for this model that I'm talking about. Okay, HS 376, and only outer panel generates electrical power. So this is how exactly it was built. Okay, so tremendous effort actually in this field of communications. Okay, where you can see people actually working hard in order to make sure that their satellite systems, all the money that is put in there, okay, shouldn't go waste, because this is a huge investment. Okay, it's not just about just few dollars or few rupees. Okay, it's a huge investment, and in fact, few companies take the help of the government as well. Okay, so the dimensions are given here. This is about 216 by 660 centimeters, and the outer cylinder. Okay, this cylinder that you see, the outside the black one. Okay, is telescope over the inner during launch sequence. Then the power capacity. Okay, it is capable of about 940 watts DC power. Those batteries that you see in our cell phones are all in milliamps, 2000, 3000, 4000 maximum. Okay, we can see about 7,000. So 7,000 milliamps, so which is about 7 amps, right? Uh, but here we cannot have that levels. The battery level should be much higher. Okay, and see, even after 10 years, its efficiency, as I told you, we were using this lithium ion. Okay, then we started using nickel cadmium. Okay, then you know a lot of enhancements are actually happening, and as I was mentioning in the previous class, graphene is also extensively researched. During eclipse, two nickel cadmium long life batteries are used with 830 watts, so this can be recharged from 0 to 100% in 16 hours. Okay, so that's the recharge time that it takes. Some more information given with regards to power management. Just have a look at it. So it's important to note here that you know the full complement of solar cells is exposed to sunlight. So maximum exposure, we should make sure that it gets maximum exposure to the sunlight. So if in case the panels are designed in such a way, maybe circular, okay, or probably elliptical, then what is going to happen is the surface, okay, the area of exposure is going to be less. So here my idea is to have more exposure area. So for that reason, what I'm going to do is I'm going to design as you see here. Okay, it's normally rectangular or square in shape, where I get maximum exposure of sunlight when the light falls on it. Higher powers can be achieved with solar panels in rectangular solar cells. Right? So solar cells are folded during the launch phase. So when we are launching it, okay, it is just like the wings of a bird. Okay, it can actually open up and it can accept the sun rays. whenever needed. Okay. Some more information with regards to the solar cells. Solar cells must be folded during launch phase and extended when in geostationary orbit. So as soon as it comes to its orbit, okay, we should make sure that these wings open up. Okay, so once these wings open up, it will start charging, and the reason why it starts charging because it has solar cell, and this solar cell will in turn, mm, power up your satellite. Just go through this 2 3 points which I am added here, which is with regards to the power management itself. So you can imagine the stretch that happens, okay, when they are folded, okay. It can stretch to about 67 feet, okay, which is about 20 meters from one end to the other end, so which is too huge, right? So they are capable of greater power output than cylindrical arrays, okay. Can someone tell me why is it more capable, the rectangular ones? Because, why is it so? Because the exposure, right? So with the rectangular one, I get more exposure, right, than the cylindrical one. So when I compare, okay, when I compare the power capacity of cylindrical and solar uh, sail satellites, the crossover point is estimated to be about 2 kilowatts, where the solar sail type is more economical than the cylindrical type. Now, one more thing that you can remember is it is hard to manufacture the cylindrical type of panels, okay, but it's very simple to manufacture a rectangular type of panels. Okay. So this will be our last slide for the class, okay, and you can see here as to how the eclipse happens, okay, towards the left hand side. You can see the eclipse time, okay, and towards at the bottom, okay, you can see the day of the year. So as it passes, okay, as the days of the year is passed, okay, you can see that you have a full shadow. Okay, full shadow is the inner one and half shadow is the outer one. Okay, so at 2 points of time in a year, okay, so this happens, so 60 to about 105, okay, close to 110, then here about 245 to about 290, right? So these are the satellite eclipse time as a function of current day of the year. Okay, so how much minutes that it can last for? So you can see that it is, the full shadow is lasting for about 60 65 approx, right? And the half shadow is about 70 minutes. Okay, and this happens at the 80th and 90th day. It's going to be peak. Okay, so yeah, so so this is what I had planned for today's class, okay, with regards to introduction to your third module, and the power management and the batteries involved, and how the payload is taken, and who is responsible of taking the payload, okay, all this information. So students, what we will do is we will catch up in the next class, okay, and we will continue discussing on the specifications. Okay, there are a few more examples that I need to talk about. Okay, for example, satmix 5, okay, one of the major service providers, and yeah, this is how you can actually see the rectangular panels which opens up just like wings, okay, and the sun rays falls on it. Once the sun's rays falls on it, okay, light is a form of energy, and the cell starts charging on the left hand and the right hand side of the satellite, and the power is delivered to this payload. Okay. So, so this is what I have decided for today's class. I will be sharing in the link, okay, and you guys can give in your attendance.